Limits and continuity. In this section, we will learn the definition of a limit, as well as the definition of continuity. With that, we can then look at the precise definition of the derivative. We will look at many examples of how to apply these definitions to algebraic and numerical examples. The limit. The notation that we use for the limit looks like what we have over here. So LIM is limit as x approaches c. So as x gets closer to some number, the function f of x, or the y value, will approach some y value which we call L. So the expression to the left means that f of x can be made as close to L as you would like by taking x sufficiently close to c. Let's look at an example of how this works. So down here, we have the limit as x approaches 2 of x squared. So what we're looking for is the y value of x squared here when x gets really close to 2. So what does that mean? Looking at our table here, we can take values closer and closer to 2. So when x is 1.9, x squared is 3.61. When x is 1.99, x squared becomes 3.96. When we get to 1.999, so now we're getting really close to 2, the x squared value is 3.996. We can also approach 2 from the other side. So if we get sufficiently close from that side, we look at 2.001, which gives us a value of 4.004. By looking at the values at 1.999 and 2.001, we can see that we are getting pretty close to a certain number between these. Can you see what that number is? Well, although we cannot definitively say quite yet, a limit of 4 would be a good guess for the above limit. And we know that if we plug 2 into x squared, that we get 4. We have to be careful though, because with a limit, you're taking x to be close to 2, but you can't just plug the 2 in until we know a little bit more about continuity. There are certain cases where you can and can't just plug things in. We'll look at some of the cases where you can't. I want you to notice that the limit describes the behavior of a function near a point. So let's use the graph to estimate the limit as x approaches 0 of 2 to the x minus 1 over x. I want you to notice in this example that we can't just plug a 0 in for x, because then we would be dividing by 0, and we know that in mathematics that's a big no-no. So what we're going to do first is we're going to use our calculator to get a graph of this function. I want you to note that our function is undefined at 0. You're going to have a little hole when x equals 0. I also want you to notice that our function approaches the same y value from the left and from the right. So even though there's a hole there at 0, it's approaching that same y value. So what we're going to do is we're going to use the zoom function on your calculator to see what that value is, even though there's a hole there. Because when we take a limit, we're not looking at the value at 0, we're looking at the value as you approach 0. So by using the zoom function on your calculator to get closer and closer, you'll find that it approximately approaches 0.693. So that means that the limit as x goes to 0 of 2 to the x minus 1 over x is approximately 0.693. So it's important to remember that even if you have a hole somewhere, the limit still exists because you're not looking at the point exactly where x equals 0, just near x getting closer to 0. So now let's look at how we would estimate the limit as h approaches 0 of 3 plus h squared minus 9 over h. Again, we can't plug in 0 because then we'd be dividing by 0. So first we can look at this numerically. That's what we did before. So now we want to look at values as we get closer and closer to 0. So if we look from the left side, as we call it, so negative numbers, which are right below 0, and we look at negative 0.1, negative 0.01, and negative 0.001, we get the corresponding values that we get from plugging those values into this function right here. You can do that part on your calculator. And we get 5.9, 5.99, 5.999. We can also look at this from the right side, or the positive side. So as we approach 0 from the right, we have 0.1, 0.01, 0.001, and our values that we get when we do that are 6.1, 6.01, 6.001. So looking at these two values as we get closer and closer to 0, we would say that these appear to be approaching 6, and that would be a really good thing to say. Now, algebraically, things are a little more tricky. So here, what we can do is we can start by multiplying out this 3 plus h squared. So all I did here was FOIL that, and that gives me 9 plus 6h plus h squared. And remember to add the minus 9 from over here. We didn't do anything with that. But notice now that we have a 9 and a minus 9, so those will cancel. That leaves us with 6h plus h squared over h. Well, notice all the terms here have an h in them. So if we factor an h out in the top, we have an h times 6 plus h over h. Now we can cancel those two h's, the one we factored out and the one on the bottom. Well, that's fantastic because now we don't have an h on the bottom, which was presenting the problem for letting h go to 0. So now we have the limit as h goes to 0 of 6 plus h. Well, now we don't have this problem of it being in the denominator, so we know that as h gets closer and closer to 0, this goes to 6. So now, I want you to think back to section 1.3. We looked at average rate of change, which was given by the formula f of b minus f of a over b minus a, and that gave us the slope of the secant line. We used the average rate of change to talk about the instantaneous rate of change. If you remember, when we tried to find the derivative by estimating, we looked at the secant line on the left and the right of our tangent point. Imagine we want to look at a point x and a small distance h away from x. So our a is x, the point we want to look at, and our b would be x plus h. We just want to be a small distance away. So we can write this equation using our a and our b as these values, plugging them into the average rate of change. It'll now look like f of x plus h minus f of x over x plus h minus x. Notice here that in the denominator we have an x and a minus x, so those will cancel. So this simplifies into f of x plus h minus f of x over h. Now remember, what we're looking to do is get as close to x as we can, which means that this small distance h needs to get smaller and smaller. So now what we want to do is we want to let h get closer and closer to 0, because that means we're a smaller and smaller distance away from our point x, which means that our secant lines are getting closer and closer, and we're looking towards getting that tangent line, or finding the instantaneous rate of change. Well, we've done this before in 2.1 and 2.2, but now we want to express this as a limit. So we can write this as the limit as h goes to 0 of f of x plus h minus f of x over h. So again, by letting h get closer to 0, we're minimizing the distance away from x. So we're getting closer to that tangent line. And remember, when we find the instantaneous rate of change, the notation looks like this: f prime of x, also known as the derivative. So now we can use this to compute some things numerically. So using the definition we just learned, if we want to find the derivative of f of x equals x squared plus 2x plus 1, we start with our basic definition we had on the last page. So the limit as h goes to 0 of f of x plus h minus f of x over h. Remember from composite functions that f of x plus h means we're going to plug x plus h in everywhere we see an x here, and f of x is just the original function. So we start by plugging in an x plus h everywhere we see an x in the original function. That's this part right here. Then minus f of x, so minus the entire function over h. Next, we want to square out the x plus h, and we want to distribute the 2 through. When we FOIL, we're going to get x squared plus 2xh plus h squared. When we distribute the 2, we're going to get 2x plus 2h plus 1. And then we still have minus, and remember, you want to use parentheses for the whole function, so minus x squared plus 2x plus 1. Now we want to combine like terms, so I want you to notice that we have an x squared and a minus x squared, so those will cancel. We have a 2x, and we'll have a minus 2x, so those will cancel. And we have a 1 minus 1, so those will cancel. So once we cancel out those terms I just mentioned, what's left? There's an h squared from right here. There's a 2xh from right here. and there's a 2h from here. Everything else is canceled out, and we still have our h on the bottom. So now notice every term has an h in it. Well, that's really handy, because now what we can do is we can factor out an h. So by factoring out an h, we're left with an h plus 2x plus 2. So I pulled an h out of each term in the numerator. So now we have an h in the numerator and an h in the denominator. Those can cancel. Well, that's fantastic. Now that we've canceled, we don't have the problem of the h in the denominator. So we look at the limit as h goes to 0 of h plus 2x plus 2. Well, as h goes to 0, that term will disappear, and we'll be left with a 2x plus 2. That's the derivative of our original function. So that means if the original function is x squared plus 2x plus 1, our derivative now is 2x plus 2. And again, we did this by applying this derivative formula right here with our limits. So now we need to talk a little bit about continuity, because continuity is what allows us to be able to plug a number right into a function. So a function is said to be continuous on an interval if its graph has no breaks, jumps, or holes on that interval. So if you can draw a graph without picking your pencil up off the paper, it's probably continuous. So let's look at the popular functions that are continuous. So here, x squared plus 5x plus 2. So that tells us here polynomials are going to be continuous. So that's your x squared, your x cubed, your x to the fourth. As long as you're not dividing by anything and it's a straight polynomial, it's continuous. Exponential functions are also continuous. So e to the x, 10 to the x, 20 to the x will also be continuous. Trigonometric functions sine and cosine are also both continuous. Let's look at some functions that are not continuous. So 1 over x. So if you have some sort of polynomial in the denominator, it's not going to be continuous. This particular function is not defined at x equals 0, so it's not continuous because it doesn't exist there. F of x equals the natural log of x. So that's not defined when x is 0 or negative. So for the above examples, it's important to note that these functions can be continuous on an interval, but not everywhere. So many functions that are not continuous everywhere can be looked at very simply by applying an interval where it is continuous. So now for the formal definition of continuity. The function f is continuous at x equals c, so at some point, if f is defined at x equals c, so that means there's no hole there, and the limit as x goes to c of f of x equals f of c. So that means if you look at the limit as x approaches the number, it would equal the same value as if you were to plug that number directly into the function. The function is continuous on an interval if it's continuous at every point on the interval. So again, if you want to look at a function that's not continuous, you can certainly find an interval where it is continuous to work with it the way you need to. So now, what we can do is we can take any functions that are continuous wherever we're looking, and now we should be able to plug numbers directly into the function. I want you to note that there's some popular functions that are continuous, which include sine, cosine, exponential functions, and polynomials. They are continuous everywhere. So these two things, in conjunction with each other, will now allow us to move into Chapter 3, where we'll learn some formal rules of derivatives that are no longer estimates.